Now we are going to introduce the second law of thermodynamics. The second law of thermodynamics does not have a single statement to describe it. It can be stated in different ways. So we are going to introduce three statements that describe the second law of thermodynamics. First, Clausius' statement. It is impossible for any system to operate in such a way that sole result would be an energy transfer by heat transfer from a cooler to a hotter body. In other words, heat cannot be transferred from a low temperature to a high temperature on its own. For example, a cold coffee never gets hot by extracting the thermal energy from the colder surroundings. It is impossible for any system to transfer the heat from a cooler to a hotter body with no effect on the surroundings. A refrigerator removes heat from a refrigerated space that is low temperature and dumps the heat to the kitchen that is high temperature. This is not a spontaneous process, but the process is possible by providing work to the refrigeration system. Thermodynamic systems have heat interactions with the surroundings, known as a thermal energy reservoir. A thermal energy reservoir is an idealized body that has a relatively large energy capacity. It remains at a constant temperature regardless of the amount of heat loss or heat gain. It can absorb or provide large amount of heat without any change in temperature. So very large bodies such as oceans, lakes, rivers, or atmospheric air can be considered as a thermal reservoir. Thermal reservoir is also called a heat sink or heat source, depending on the direction of heat transfer. For example, an air conditioning system or refrigerator transfers thermal energy from a low temperature reservoir and rejects heat to a high temperature reservoir. Low temperature reservoir is the heat source, temperature T1, and the high temperature reservoir is the heat sink, temperature T2, and T2 is greater than T1. On the other hand, heat engine transfers thermal energy from a high temperature reservoir to a low temperature reservoir. In this case, the high temperature reservoir is the heat source, temperature T2, and the low temperature reservoir is a heat sink, temperature T1. So T2 is greater than T1. Kelvin-Planck statement. So it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. We need to introduce a concept of heat engine to explain the Kelvin-Planck statement. A heat engine is a continuously operating device that converts heat into work. A thermal energy from a high temperature reservoir is transferred to a heat engine. The heat engine converts a portion of the thermal energy to work, and it rejects the remaining thermal energy to a low temperature reservoir. A steam engine is an example of a heat engine. So it uses steam to produce mechanical work. So Kelvin-Planck statement suggests that no heat engine can have a thermal efficiency of 100%. That means we cannot make a heat engine that converts all thermal energy into equal amounts of work. So even an ideal heat engine with no energy loss due to friction cannot have 100% efficiency. So some energy must be rejected to the surroundings in order to restore the engine to its original state. In other words, heat engine must interact with two thermal reservoirs, high temperature and low temperature reservoirs. Heat engines cannot interact with a single reservoir to complete a cycle. It will be easier to understand the statement using a water wheel analogy. The potential energy of the flowing water rotates the wheel. It will continue to rotate as long as the water is continuously supplied to the water wheel. But once the water passes through the wheel, it is useless. We are not using the water again that already left the wheel. The water after the wheel still has energy as it continues to flow, but we may not be able to bring it back to its original state to rotate the wheel. So we only use the potential energy difference between the initial and the final states. But we have to dump the fluid after it passes through the wheel. So back to the heat engine. Similarly, heat engines must reject heat to the surroundings to provide work continuously. That means heat input is always smaller than work output. This is the main idea of Kelvin-Planck statement. Both Clausius statement and Kelvin-Planck statements are negative statements. It is not possible to prove the statement. They are based on experimental observations. Also, the two statements appear to be different, but they are equivalent in the sense that a violation of either statement implies violation of the other statement. Entropy statement. It is impossible for any system to operate in a way that entropy is destroyed. The entropy of a reversible process remains constant, and the entropy of actual processes always increases. So we will talk more about this later after introducing the concept of entropy.